Yes, so it's time to talk about the variation of the measurement uncertainty with measurand level. And in chemical analysis, measurand level is often concentration. So I will use the word concentration in a big part of the slides here. And I seen from the some questions in the chat that there has been questions about this, so I hope we will clarify a little about this in this presentation. And the reason for having a presentation like this is that in empirical approaches and top-down approaches, we typically use data for different types of precision, repeatability or reproducibility, and so on, and sometimes also trueness data. And these data, they are calculated from samples and reference materials at different concentration levels. And in order to combine them in a correct way, it's important to know the concentration dependence. And often it's a question about, should I combine them as absolute uncertainties or relative uncertainties? And I think, at least in my opinion, this is one of the most crucial parts in top-down approaches for evaluating measurement uncertainties. And so I think this is something that really needs to be focused on. And if you look at the very typical dependence of concentration on measurement uncertainty for many instrumental techniques, it will look like something in the red figure here. And the reason for this is that we have many different types of contributions to uncertainty, and typically they can be divided into two types of contributions. In one type of contributions, they will add to the uncertainty in this way. We look on the green solid line here. It will typically add to the uncertainty independent of the concentration. Other types of contributions will add to the uncertainty in this way. We now look at the green dashed line here, and typically it will increase with concentration, like this. And when we then combine all these contributions, we will end up with something looking like in the red curve here. And this could then be simplified further to look something like this. We now look at the left figure here. So we have absolute measurement uncertainty here and concentration on the x-axis here. And typically, in a small concentration range at low concentration, the absolute uncertainty is more or less independent of concentration. And then when we go up in concentration, it will start to increase and become proportional to the concentration like this. And this is often the major part of the measurement range. Now, if we instead look at relative measurement uncertainty, this figure will transfer into this one. So this part here will now look something like this. The relative uncertainty will be more or less independent of concentration. And in this small part down here at low concentration, the relative uncertainty will increase dramatically when we go down in concentration. And when I try to explain this at my courses, I often put these two figures on top of each other like this. And then I think it becomes very clear that at this part of the measurement range, it's very convenient to have a relative measurement uncertainty because it's independent, or at least approximately independent of concentration. And here, when we evaluate uncertainty, we can combine relative uncertainties from different concentration levels. Down here, it's more appropriate to have an absolute measurement uncertainty because then the absolute uncertainty is independent of concentration. So here when we calculate uncertainty, we can combine absolute standard deviation and absolute uncertainties. Now, this is quite a useful model for many instrumental techniques, but there are exceptions to this, and I have just listed some of them here. pH will not look like this at all typically. Then it's often very convenient to have an absolute uncertainty in the whole pH range. X-ray fluorescence is, at least in my opinion, also an exception to this. It depends a little on how you evaluate your data, but typically you will have a more complicated concentration dependence like this. And there are other examples also that you will come across when you start to look at this for many different methods. And sometimes it might also be appropriate to divide this large range here into smaller ranges to better describe the real uncertainty of your method. So let's go to some reality here. What is the concentration dependence for your method? And to study this, you need large amount of data that are rarely available. But there are a few ways of handling this, and I have listed them here. So for precision, it's often interesting to look at results for duplicates that will then describe repeatability. You could also try to look at performance data in standardized methods. Nowadays, you can often find both repeatability and reproducibility data at different concentration levels in the methods. Sometimes, not so often, you can also look at precision data from proficiency testing schemes, and that will then describe reproducibility. For trueness, it's a little more complicated, at least in my opinion. Well-defined bias and recoveries at different concentration levels are rarely available. So often you will end up with looking at precision data. And I'm going to give a few examples of these three here, what it can look like. And we start with the first one here. Here we look at results for duplicates. So it's repeatability we're talking about. And in this example here, it's from determination of ammonium nitrogen using a spectrophotometric technique. And I think the data here are actually taken from the NOR-test report here, if you want to look at the data yourself. And what I have done here is that I have, for each point here is from a sample. And for each sample, I have calculated the maximum value minus the minimum value divided by the mean for the two replicate results. And then we have concentration here on the x-axis. And here I have a log scale here, but it's just to keep the size of the x-axis reasonably short here in the figure. And now we will look at the pattern here. We don't care about the individual points. It's the pattern that is important here. And my interpretation of this is that in this range, say from 25 or 30 and higher, this here, that is actually describes what can be called the relative difference between the replicates. It will be fairly constant and more or less independent of concentration. So here, in my opinion, this indicates that it's appropriate to have a relative uncertainty here. If we look at the lower part of the concentration range here, we see another pattern. We end up with points higher up here. And this indicates that it's appropriate to have an absolute uncertainty down here. And we could keep this in mind. This was what we were looking at the previous slide here. This shape here is more or less the same as you have here. And here we have just looked at repeatability. It's just a part of the overall uncertainty, but it turns out it's quite a good indication of what the uncertainty dependence look like. We should see a little more about this in the next slide here. Here we're looking at performance data in standardized methods. And many standard methods nowadays, they have repeatability and reproducibility at different concentration levels. And I think I found that really useful many times to find out about the concentration dependence here. And I've done this for a lot of standardized methods. I just picked one example here. I don't actually recall what method it is now, but that's not so important. It's just an example of what it could look like. So here we have repeatability, and the field symbols here are standard deviation for repeatability, and we can see that it increases more or less proportional to the concentration. If we look at the relative standard deviation or coefficient of variation, it's the open symbols, and then it's the right y-axis here. And at least in my opinion, it's fairly constant and independent of the concentration. There should be a there should be an open symbol up here at 100 milligram per liter also. I think it's actually overlapping with the fill symbol here. And if we look at the reproducibility, we will see that it's very similar pattern to the repeatability. So this again shows that repeatability is quite a good estimate of what the concentration dependence for the uncertainty will look like. And reproducibility is often a very, very good estimation of what the uncertainty will be for the whole method. So we should also say something about data from proficiency testing schemes. I didn't really have a good example of this. I used it a few times, but my experience of this that it's not so easy to use, but it's something you could try. I think often proficiency testing schemes, the concentration tend to not vary that much from year to year. So it's rarely that you will find any useful information about this, but sometimes it will happen, and it's something you can try to look at. So we should also say something about this. There is something called Horowitz trumpet, and it's a quite old relationship that they found when they compared interlaboratory studies. They took the standard deviation from interlaboratory studies in food analysis and plotted against concentration, and they came up with a concentration dependence looking like this. And here you don't have a perfect proportionality, but at least in my opinion, it's still quite good. And we should keep in mind here that here, this relationship is for very large concentration ranges and includes variation between different methods. The standard deviations here are coming from different methods, different instrumental techniques at different concentration levels. But still, at least in my opinion, this indicates there is a very strong proportionality between reproducibility and concentration. And I think we are now coming to the last slide here. This is also something I like to mention here. I think it's related to the concentration dependence. Uncertainty can be expressed as coverage intervals. And when doing this, the relative uncertainty, and the relative uncertainty is approximately independent of the concentration. And the combined standard uncertainty is above approximately 15 to 20%. It is necessary to consider asymmetry in the uncertainty coverage interval. And this is something that will be discussed tomorrow. I think there will be 2 presentations tomorrow about this. So I'm not going to say more about this now, but it's something that will be brought up tomorrow. And I think this was the last slide, so the end, and thank you very much for listening.